Piping Vibration Quantitative Smallbore Connections or SBC LOF Assessment, Analyzing Loss of Function in Pipework Systems. Purpose and Scope of SBC LOF Assessment. The quantitative SBC LOF assessment methodology, as outlined by the Energy Institute, is designed to evaluate the likelihood of failure, LOF, for smallbore connections, SBC, in pipework systems. These connections are particularly vulnerable to vibration-induced fatigue, which can lead to catastrophic failures if not properly assessed. The methodology provides a structured approach to determine the risk level associated with each SBC by considering both geometric and locational factors. The assessment can be performed independently or in conjunction with mainline LOF evaluations. If uncertainty exists regarding excitation mechanisms such as slug flow or environmental loading, a conservative approach is recommended by assigning a mainline LOF of 1.0. This ensures that the SBC assessment accounts for worst-case scenarios. The process also emphasizes the importance of avoiding coupling between SBC natural frequencies and tonal excitation frequencies, which can amplify vibration effects. Ultimately, the goal is to identify high-risk SBCs and implement mitigation measures, such as bracing or redesign, to enhance system reliability and safety. Two-stage assessment process. The SBC LOF assessment consists of two primary stages, geometric LOF and location LOF. Geometric LOF evaluates the physical characteristics of the SBC, such as its type, dimensions, and structural configuration, to determine its susceptibility to vibration-induced stress. Location LOF, on the other hand, considers the SBC's position on the main line and its proximity to excitation sources. The final SBC modifier is calculated as the minimum of these two values, reflecting the principle that both poor geometry and poor location must coexist for an SBC to exhibit a high likelihood of failure. This conservative approach ensures that neither factor alone disproportionately influences the risk assessment. The methodology also accounts for cases where the mainline LOF is unknown or exceeds 1.0, in which case the location LOF defaults to 1.0, making geometry the dominant factor. This structured process provides a clear framework for engineers to prioritize SBCs for inspection and remediation. Classification of SBC types, geometric assessment factors. The geometric assessment methodology categorizes SBCs into four distinct types based on their structural configuration: Type 1, cantilever; Type 2, continuous, in and out same main line; Type 3, continuous, with intermediate supports; and Type 4, continuous, between different main lines. Each type exhibits unique vibration characteristics and requires tailored assessment procedures. Type 1 SBCs, for example, behave like cantilevered beams and are highly sensitive to mass distribution and branch length. Type 2 SBCs involve continuous connections within the same main line and require splitting into two cantilever-like sections for evaluation. Type 3 SBCs incorporate intermediate supports, which alter natural frequencies and reduce vibration risks but necessitate separate assessments for initial and subsequent spans. Type 4 SBCs, which connect different main lines, are uncommon and discouraged due to significant static stresses arising from differential movement. Understanding these classifications is critical for accurate LOF estimation and effective risk mitigation. The geometric assessment process involves evaluating several key parameters, including fitting type, number and size of valves, SBC minimum diameter, parent pipe schedule, and overall branch length. Each parameter influences the SBC's stiffness and natural frequency, which in turn affects its susceptibility to vibration-induced fatigue. For instance, fittings such as weldolets or sockelets exhibit different span factors, impacting allowable span lengths and LOF scores. Similarly, larger diameters and heavier valves increase mass, lowering natural frequencies and amplifying vibration risks. The methodology employs flowcharts and tables to assign LOF scores based on these characteristics, ensuring a systematic and repeatable evaluation. By quantifying these geometric factors, engineers can identify SBCs that require reinforcement or redesign to prevent failure. Determining location LOF. Location LOF assessment focuses on the SBC's position relative to excitation sources and structural supports. Key considerations include whether the SBC is attached near valves, reducers, bends, Ts, or midspan sections of the main line. These locations often experience higher dynamic loads and vibration levels, increasing failure risk. The parent pipe schedule also influences LOF, as thicker schedules provide greater stiffness and resistance to vibration. The methodology uses a scoring system to calculate the mean of location-based factors, resulting in a location LOF value. If the main line LOF is unknown or equal to or greater than 1.0, the location LOF defaults to 1.0, indicating that geometry will dominate the final assessment. This approach ensures that SBCs in high excitation environments receive appropriate attention during risk evaluations. Calculating the SBC modifier. The final step in the quantitative SBC LOF assessment is determining the SBC modifier, which represents the overall likelihood of failure. This value is calculated as the minimum of the geometric LOF and location LOF scores, based on the principle that both poor geometry and poor location must be present for an SBC to exhibit high risk. This conservative approach prevents overestimation of risk when only one factor is unfavorable. The SBC modifier serves as a critical input for maintenance planning, guiding decisions on whether to implement corrective actions such as bracing, redesign, or enhanced monitoring. By integrating geometric and locational considerations, the methodology provides a comprehensive and balanced assessment of SBC integrity, supporting proactive risk management in complex piping systems.